Again, guys, good morning, and we are back to talk about implicit differentiation. And before I speak, perhaps one of you would like to comment about this idea. What is implicit differentiation about? What is the strategy? Yes, Ibad. Okay, what Ibad is saying is pretty good. So that's the idea. Many functions will be given implicitly inside of an equation, as in, for example, x squared plus y squared equal to 25. That solves y as a function of x. Good, but only, and by the way, not globally, very likely just locally a function of x within some vicinity. Good. And the explicit method will be to first find that function and then differentiate it. So here is where we do that. We solve this equation. We see that y, where I want to find the tangent line, is positive, and I generate y equals root of 25 minus x squared. Having found the function, I take the derivative, and I have this formula. So what the implicit method is to bypass this entire procedure and assume that the solution was already obtained, and then take the derivative. So in other words, whenever in this case we see a y, we imagine that we see a formula. So we imagine that we actually see the formula that would have been obtained had we solved the equation explicitly. Good? But when we differentiate such a thing, we do that using the chain rule. So in this case, let's say it's y squared, so the derivative is 2y y prime, because it's a square function holding a function that whose formula we just do not see. So we can only say y prime for it, or the derivative of the inner function. And that's how we proceed. Good? That's the idea. Do you all understand the y prime thing, guys? Please confirm in the message that you understand where the y prime is coming from. What's the idea there? Let's see. Still only 14 individuals confirmed, and I have here 30 or so registered. All right, a few more added. So you have to know that, guys, when you leave this office hours, when you don't go to them and you don't know that, that's sad. You have to know that. Okay, and then we solved a few examples where we did it implicitly and explicitly, just to give you a sense that when you do that explicitly, you see a formula, and when you do that implicitly, you pretend you obtain that formula and work from there. Yes, and the results are the same. And then you see in this equation, the explicit solution would be very complicated, and it would take you a long time to derive. Again, I can show you how you can derive this formula. You need to know what is the cubic equation. It's a pretty important equation. So if you are interested, you can stay after class. I can explain. But we can bypass that. Even if I obtain the solution, which will take some time, it looks ugly. I don't like differentiating it. So it's much easier to just take the derivative and solve. And that's what, and let's say equations like this one, well, you cannot even find a way to solve them too well. All right, the solution will be very complicated, and it's not even clear how to proceed. But if we imagine we obtain the solution, we can take its derivative and get the derivative formula. And then I ask you to take your time and find the derivative. Okay, I hope you studied over the weekend and you practiced it a little bit. So let's do it now. Let's solve problem D. Solve problem D. See how fast you can do it. Are you ready? I'm giving you a head start. We will compete. See if I can solve it faster than you can. So we're solving D. Nice to see you, Alexa. I'm done. How are you? All right, good. Good, good. All right, guys. Let's get going. So if you want, we can practice such problems in office hours. I'll give you more time, but I have to move. So here is problem D. Here is in slow motion. So we take the derivative of left. We take the derivative on the right. The derivative of 1 is 0. Derivative on the left involves product rule. Two product rules here, right? This product rule, derivative of x sine y will be sine y plus x cosine y times y prime. Do you see where the y prime comes from? It's really sine that contains a function that I just do not see its formula. So I write y prime. Plus the derivative here, it's y prime sine x plus y cosine x. Here I take the derivative of y first and don't touch sine, and add y y times derivative of sine, which is cosine here. Good. And once I do that, I will group the y primes on my left and move everything else to the right. Factor the y prime and simplify. Good. And you have lots of other examples of the same sort. Okay, so this you practice doing at home. Let's move on. Now, how am I doing it so fast? I mean, you agree that I do it fast, yes? How am I doing this? Why can I do it so fast and you do it so slowly? Any ideas? Maybe, but that's not an explanation. I mean, it's very, box, that's it. No, that's not so. It's not because I have the answer. And Zainab, okay, interesting. Interesting question. Now, the reason I do it fast is because I understand calculus 3, right? And because I understand calculus 3, I can figure out other ways to solve this question very rapidly. And the idea is that, first of all, every question here, every formula here can actually be thought as a constraint on a function of two variables. So for example, if I have x squared plus y squared equal to 36, then I can think of, I can move everything to the left and I can think of this as a function. I think of f of x equal to x squared plus y squared minus 36, this function, equal to 0. So it's a function of two variables that was constrained to be equal to 0. You follow what I'm saying? So what would be the function of two variables for D? Can anybody write just the function of two variables for D? In other words, in Calc 3, I can see that this is some function involving two variables equal to 0. What would that function be for D? Please type in the comments. The question is this. I'm showing you one of my tricks. So first, you have to understand that every implicit differentiation formula can be written in this form: a function of two variables equal to 0. So for example, if I have x squared plus y squared equal to 36, I can think of the function of two variables as x squared plus y squared minus 36. I can move everything to the left, and I have this function equal to 0. Do you understand what I'm saying? So I just want to know, for those examples, can you figure out what's the function involving two variables that's equal to 0? Very simple question. So what is it for D? Yes, so D is f of x, y equal to what you wrote, precisely, Ibad. And what about the rest of you? So can you write it, the rest of you guys? Yes, Stephen? And the rest of you, only 2 people? Yes, wonderful, Alexa. Good, good. Okay, that's the function. You can do that with all of them. Just move everything to the left, and that will be a function of 2 variables, okay? You see here I did it, I gave you plenty of examples where I just move everything to the left, and I mentioned what is the function. So it's a function of 2 variables equal to 0. So that equal to 0 is a constraint. Yes. Yes, Jacqueline. Wonderful. Good. So here is what I do. Now, why it works, it will take me too long to explain to you, okay? But and be very careful about using something that you do not know. But you can use this to check your work, okay? Here is what I do. I take the derivative of this function of 2 variables as if x is the variable and y is a constant on the numerator, and divide by doing the same, but I take the derivative with respect to y. I pretend that y is the variable and x is the constant, and I write a minus in front, and that will be correct. So let me show you how I solve this problem. Okay, let's do problem A, and you will see why I'm so fast. Perhaps, right? So instead of doing the procedure you are doing, I do the following. I first move everything to one side and say equals 0. Okay, then I write the dy dx equal to minus, and then you have to be careful here. So here, be sure, guys, that you don't understand this procedure. So be sure that you understood what I explained before, the implicit differentiation as I explained it. You hopefully understand. Now, what I do is that I take the derivative of this expression, of the expression on the left, as if y were a constant. That's what I do in the numerator. So the derivative when y is a constant, it's e to the y minus sine x. So it is e to the y times minus sine x. And then the derivative of sine, it's minus cosine xy. And if y were like the number 5, it's a constant, then what you would see is that y will jump out. So that's the derivative of the numerator. The derivative of the denominator will be the same, but now I treat x as a constant. Y is the variable. So that would be derivative of e to the y, where y is the variable, is e to the y cosine x. It looks to me like a function multiplied by a constant in that sense. Minus cosine xy, and this time y is the variable, so x jumps out, and that's the solution. That's the solution. Let's try that.
Wait.
Yes?
Where did you get the y in front of the cosine?
Because this is how I look at this question. So for here, y, so this is like cosine of x multiplied by 5. Y is a constant. So when I take the derivative, so it was sine, not cosine there. So first it's this. I treat y as if it were a constant. When I take the derivative by chain rule, it's going to be cosine of x multiplied by 5. The derivative of the inside will put a 5. Right? Or you can put the 5 here if you prefer, right? Derivative of x times 5 is 5. So in general, if y is that 5, it would be y. Okay, so it's a constant. So make sure that, of course, if you decide to practice this technique, that you are aware of the explanation I gave before, because that you still understand. Why I do this procedure, you do not understand. I can explain that, of course, but it will take me quite a lot of time. I will have to explain to you what are partial derivatives and the like. Okay, so if you, here is what I'm one thing that I'm trying to say is, if you know more mathematics, then it makes things a lot easier. One thing is, because I know something, I can actually get the results a lot easier. It's much better, guys, to learn and know the material than to memorize it. Even if all you care is just passing, it's much easier to do that. Okay, let's try this question. I will raise it. Could you please do B? It's pretty simple, and do B using my strategy. Let's see if you can do that. But at home, you practice what I explained, right? Practice to solve equations, just as I explained it. Ping, you forgot the minus. Other than that, you're right. Kirill, you got it. Ibad, you got it. Jacqueline, you got it. Yes, but you see, so you of course know how to do it using the previous method. I want to see that you can do it using the shortcut. On the exam, I want to see that you understood what was explained, because this procedure I just kind of gave you in thin air. You don't know why it works, right? So I prefer when you use things that you know how they work. You can use this to verify that your solution is correct, right? You can add it to the exam. I can add extra points for writing it on the exam, but know that I suppose if on the final, if you remember this formula, they might not check how you do it, right? You can do it fast this way. When they ask you an implicit differentiation question, you can do it this way.
Question for
Yeah.
like the correct answer. Where did you get the negative from?
Well, that's the problem. You see, why do I get the negative from that? That's the formula for implicit differentiation. I mean, I kind of wrote what happens here, but that involves partial derivatives. You see, so this expression, why do I do this, might not make any sense to you. You see, it happens to be this formula. So I never remember. I might have forgotten the minus. I just can derive it in 2 seconds. I know why that's true. That involves ideas from Calc 3. Okay, so it just ends up that the formula dy dx. So first, again, let me show you one more time what happens. I look at this expression and I write x squared plus y squared minus 1 equals 0. In that case, doesn't matter. The minus 1 will not do anything. And then I write dy dx. I put a negative, and in the numerator I pretend that x is the variable. In the denominator I pretend that y is the variable. So what I will get, it's like x squared plus 5 squared minus 1, something like that. So I will get 2x on the numerator, and on the denominator I pretend that x is the 5. So I take the derivative with respect to y. So I'm not considering, you see, so don't get confused. Don't allow your brain to melt, right? Y is supposed to be a function of x, but in this procedure, when I apply it, I don't consider that, you see? In this procedure, when I apply it, I just see y as just a variable of itself, x is a variable of itself. And what I write is simply 2y. Good? Let's see if you can do very fast. In other words, what you can do is, guys, is this: verify that that's what you will get if you carry out the calculations as I taught you, as I explained that it worked, right? So let's do D. Together, your goal is to quickly find the derivative dy dx. And we can see if that result is the same as what I do using the prior method. Here you forgot the negative. Actually, you are right. Yeah, Kirill, you're right. My apologies. Perhaps. Okay. Okay, guys, let's do it together. So first thing is to write 4 cosine x sine y minus 1 equal to 0. It will, when it's a constant, it will not do anything, but then I write dy dx equal to minus, and in the numerator I pretend that it's sine of pi or something. I don't know of what, right? Of pi over 2, just a constant. So I take the derivative, so you would get minus 4 sine x sine y. I'm not using the product rule. I think of y as a number. On the denominator, I think of x as a number. So 4 cosine x is just a number. Derivative of sine is cosine. So I have 4 cosine x cosine y. And as Kirill noted, the negatives disappear. And I simply get sine x sine y divided by 4 cosine x cosine y, and that's the right solution. Okay, you wrote it down, guys. It's sine x sine y. There's no 4. I forgot to erase it here, right? Cosine x cosine y. Now let's see how to do it using the long-winded method. You can simplify it. Yes, you can. You can write it even better as tangent x tangent y. Very nice, Leaky. Good that you observed. That's even better because fewer symbols written. Very good observation. Wonderful. So let's do it using the long-winded method. Are you ready? So it's 4 cosine x sine y. Okay. Here is how this problem is supposed to be solved. So we take the derivative of 4 cosine x sine y, and that would be the derivative of I believe 1 or whatever other number there. And what do we get? The derivative here using the method I taught you, it's now product rule. Do you agree? Product rule, because here I see a formula instead of y. So what I'll get is minus 4 sine x sine y plus 4 cosine x cosine y, and don't forget the y prime, right? Equal to 0. So what I get in this case is that y prime is equal to 4 sine x sine y divided by 4 cosine x cosine y. Same thing. In this case, of course, it's fairly simple. Good? You see, I got the same thing as if I were to use my Calc3 method, but in general, the Calc3 method is faster. All right, moving on. All right, guys, here is your next task. So in general, maybe there is something you might be worried about, but let's see. Look at this expression, guys. dy dx is what you want to find. X squared minus 2xy plus y squared equal to minus 10. What's dy dx? What's the derivative of y prime? Okay, Kirill says 1. What about the rest of you? What do you say? Lake says 1. And what more? Can you add? Three people said 1. Oh, interesting. Interesting, Ibad. Okay. Continue, guys. One. All right, so I mean, I wanted, of course, more solutions. I don't know, guys, why so few of you have responded. I have 1, 2, 3, 4, 5, 6 out of 30. Come on. Okay, let's see where we are stuck. Okay. So guys, you see, one reason some of you might be stuck, you need to be fresh on basic algebra, right? So in office, we can practice lots of those. In class, I have, unfortunately, this class should have been twice as long, truly, than to cover the material very well. All right, so I wanted all of you, of course, to do that, but one person here answered it correctly. The answer is it's ridiculous. This equation defines nothing at all. You could have said y prime equals to 1, but you would be wrong. Well, why wrong? Because this equation is meaningless. This is a quadratic. It's a perfect square equal to -1. Look at it. If I simplify it, it's x minus y squared equal to -10. There is no solution for real numbers. Ibad, you had it right. Congratulations. So in general, you see, don't just solve away, because maybe everything you're doing is entirely meaningless without thought. I will not be catching you like this for the exam with implicit differentiation problems. So you can feel safe to solve them, even if somehow solution ends up not being meaningful. I will actually make the solution meaningful. There is an actually very deep result. It's called implicit function theorem, which tells you that if you can find a solution to this function f of xy in this, you need calc 3 to explain that, right? If you can find a solution at some point, then there will be a function locally near that point. So if there is if there are some numbers that will make the equation work, that then doing this implicit differentiation process is not meaningless. You understand what I'm saying? So that's a very deep result, very difficult to prove, one of the hardest differential results for calculus. And you do that not just for single variables, you do it for higher variables. So for instance, here is what I'm trying to say. Look at this equation. The equation sine of pi xy plus xy equal to 3y has a solution x equal 1 and y equal to 1/2. If I plug x1 and y 1/2, this will work for the numbers x and y. Okay? Now, because the derivative with respect to y will end up at 1 1/2 to be equal to -2, which is not 0, y equals y of x is meaningful. There is a function locally. Okay? So why that is, I'm not going to bother you with it, not in this class. It's beyond our scope. But just to mention, right? It's important to know that we are not doing something meaningless, and that actually, in principle, you can find a solution, and that solution will be smooth or differentiable function. All of it is covered by this very deep result. Good. We are done with this topic. What comes next? Inverse functions. So that's a very important topic. Let's hope we can cover it fairly quickly. First, recall that inverse functions are analogous to the undo process. So when I say 3x plus 6, it means a number multiplied by 3 and then plus 6. That's what happens to the input. What would have been the undo? The undo is to bring it back to the raw to the raw input. So what I have to do is I have to subtract 6 and divide by 3. So f to the -1. Why do we use that? It's not. It's so some people make that mistake. Some people think that f to the -1 of x is 1 over f of x, but that's not what we mean here at all. Let's see if I explain that below. Do I explain that? Yeah, I'll explain that later over here. So here is an example of functions that do not have an undo. So imagine that you have a soda machine, and if you press 1, you get Coca-Cola, press 2, you get Pepsi, press 3, you get water, press 4, you get Sprite. So that function is transforming the integers 1, 2, 3, 4 into Coca-Cola, Pepsi, water, and Sprite, right? The undo operation will take, let's say, Coca-Cola and give you 1. Take Pepsi and give you 2. Take water, give you 3. Take Sprite and give you 4. Do you understand how the undo worked? Here is the description in set notation. In this direction in blue, it's forward, and then undo is backward in red, right? So Coca-Cola is 1, Pepsi is 2, water is 3. It's basically recovering the input that produced this object, that generated it. Are you clear? I go fast, so I'm hoping that you understand, guys. Now, is there an undo process for this soda machine, right? So here we have 1 is Coca-Cola and 2 is Coca-Cola. 3 is Pepsi, 4 is Sprite. Is there an inverse function for B? No. There is no inverse function for B because of this situation, right? Both input 1 and 2 produce Coca-Cola. So when I have Coca-Cola, I do not know, I cannot retrieve the input. I do not know if it's 1 or 2. Good? For the others, I can undo it, but I cannot undo it for C. So there is no F inverse. Okay, here is the definition of what is inverse. So if you have a function that takes domain A and produces elements in B and it's onto, I can define the undo. It's f to the -1 undo operation to take elements from B and map them into A. And what happens is that if you compose those two functions, they cancel each other. So f inverse of f of x is x, f of f inverse of x is x. What that means is that when I apply the functions in sequence, in any which way, I will get what I start with. So for example, if I start with 2, I apply f, and then I apply f inverse, I end up with the same thing I plugged in. You see, this means f inverse. So this is written as f inverse of f of 2. That would be f inverse f of 2 is Pepsi, and that would be 2. Yes. So with this input, look at it. I start with the input and I end up with the same input. That's what it means to equal to x. Okay. On the other hand, if I were to start with f inverse of Pepsi and apply f to it, I will get f of 2, which would be Pepsi. Again, whatever I start with is what I end up with. So they cancel each other. That's why I call it the undo operation. Okay. Now, here is what I just tried to say. The inverse of f is not 1 over f of x. Because, for example, f inverse of x is x minus, if f of x is 3x plus 6, the inverse is x minus 6 over 3. And that's not the same as 1 over 3x plus 6. Now, why do we use the symbol -1? Well, you think of exponentiation. If I multiply 2 by itself 5 times, I get 2 to the 5. Now I can use the same analogy for functions. So f to the 0 of x means apply f to x 0 times. In other words, don't apply it. It's the identity. f0 of x is x. Don't apply the function to x. You can write 0 top, right? You can write 1 to mean apply f to x 1 time. Yes, here is the function. Let's take the function so that it's precise. Let's take the function to be simple. It's just f of x equal to x plus 2. Applying it once to the input, I get x plus 2. Apply it twice to the input means f of x. The 2 means apply it twice. So it's f of x, which would be f of x plus 2. And the function just adds 2 to the input. So it's x plus 2 times 2. Yes, everybody sees that, applying it twice. So it's f applied to f. It's f applied to x plus 2. And what the function is doing is just adding 2 to the input. That's what this means. There is no x. It means just add 2 to whatever I plug in. So if I plug this thing in, I add another 2 to it. And altogether, it's x plus 2 times 2. If I apply it 3 times, it ends up being x plus 3 times 2. If I apply it 5 times, it ends up being x plus 5 times 2. Because I again add 2, and then again add 2, and then again add 2. And fn of x means apply the function n times. It will be in this particular example, x plus n times 2. Now, I have the same multiplicative property as I had for powers. If I apply fn times to fm times, I end up having f of n plus m times. That means just applied m times and then applied n times. Altogether, the function was applied n plus m times. Okay, that's why we use the symbol -1, because that means apply it 1 time less. You understand? Let's try to see if you do understand, guys. Here is my function, f of x equal to 3x. I want you to tell me what is f for. In other words, f applied to the input 4 times. What's the f inverse and what's f of -3? Okay. Okay. Be careful, guys. So you apply f to itself 4 times. Okay. Careful, Alexa. Still a small mistake. Okay. Okay, Ibad and Zainab, good. Okay, good, Zainab. Ying, good. Lisha, good. All right, let's do it together. So A, how do you do A? So first of all, what is let's consider 2 inputs, f squared or f applied to itself twice to x. So that means a function applied once to 3x. What do you do? This function, look at it. Look at there is no x. You see what it means is whatever is the input, you multiply it by 3. So you apply it twice to the 2x. So first you multiply it by 3, and then you multiply it by 3 again. So it's 3 squared times x. And if I apply 4 times, it's 3 to the 4th x. Because I don't change the x. You see, x. I just whatever is here, I just multiply it by 3. That's what this is saying. So I multiply the input by 3 4 times. Okay. Here it is. You see. So twice it's this. 4 times it's just f of 2 applied to f of 2. I did it this way. Right? Same thing. And in general, fn I just multiply by 3 many times. The inverse, what is the inverse? The inverse, it's whatever cancels this operation. So here is how I find the inverse. It's something I plug into the function, and I get back my input. You see, f of the inverse, there's the 1 of f and the minus 1 of f inverse should cancel to 0, and I should get x. That's why I have this notation. You see, the minus 1 means apply 1 less f. That's what this means. So I plug it in. All I know is just I don't know anything about the inverse in general, but I know that this function multiplies the result by 3. So it should be 3 times f inverse equal to x. You see how I reason? It's something I plug into f, and then I get the input back. So it's 3 times f inverse x equal to x, which means f inverse equals to x over 3. And f minus 3 of x means apply f inverse to itself 3 times, or this is canceling f to the power of 3 if you prefer this way, right? So it's either a cancellation of f to the power of 3 or applying the inverse with itself 3 times. And the result is x divided by 3 cubed. Because apply this, so you 3 times to itself, you just divide by 3 times. So it's x divided by 3 cubed, or 27. Okay, let's try to calculate inverses, see how good you are with this, guys, right? So what you need to do is calculate inverses for A, B, C, D, E, and F. Please do it fast if you can. So let's calculate the inverse for A first. We'll do it one by one, okay? Calculate inverse for A. You should write, all of you should write parentheses about x minus 8, I think. Otherwise, it's not clear. Stephen, anybody? I imagine I know what you're saying, but without parentheses, it's, yeah, that's right. It's incorrect without parentheses. Yes, Zakia. Yes, Disha. For B, no, X means don't do anything to the input, Zakia, cannot be. Jacqueline, you forget parentheses around x minus 8. That's right, David. All right, let's do A. All right, we had enough time for A. Here is the thought process. Okay, you can use. We're gonna have better symbols. Okay, so writing F inverse X is very cumbersome because you see you write F minus 1. It's one symbol, then minus is another symbol, then 1 is a symbol, parenthesis an X, and instead I write Y. But remember that what you're doing, if the idea is if you plug the inverse into the function, then you will get back the input. You see this? F evaluated of F inverse of the input will be the input. They cancel each other. That's the idea. So I'll just write it as Y. F of Y equals to X. You see? So, and then what is F of Y? F of Y is 5Y plus 8. So you see, in school, you remember, maybe you learned it in school, you were taught to swap variables. You were saying, it would say y equal to 5x plus 8. And then you would say, oh, just simply say x equal to 5y plus 8. and then solve for y. That's how you were taught to do it, I think, in school. Am I right? Have you been taught that in school? Write to me if yes, quickly. Now, the thing about it is very often you kind of know the procedure, but do not understand what is the idea behind it. You don't swap anything. What it is that you are plugging into the function the inverse, and you just label it as y because it's more convenient to write than f inverse. Okay, the logic that's happening is this. You understand? You plug the inverse function into f. There's a function, you plug the inverse function, and you get x. That's the x that you consider supposedly swapping. There's no swapping going on here. It's just the input, yes? And labeling the inverse function as y so that you don't have to write this notation. So what you end up having is 5y plus 8 is equal to x. And it looks, if you wrote y equal to 5x plus 8, like you swapped. But that's not the same. That's not correct. That's not the same y, you understand? When you say y equals 5x plus 8, and when you say 5y plus 8 equal to x, you are actually changing the meaning of x and y. What you are truly doing is taking the function, plugging the inverse, and I just label it as y, and receiving back the input. This is what you're doing. Clear? This is actually what you're doing. There is just only x here. And then I just solve for the inverse, because in this case I have 5 times the inverse plus 8 is equal to x. So x minus 8 divided by 5 is my inverse. Good? Now, if you understand, please do problem B quickly. What's the inverse of 1 over x? Thank you, Leiki. Gabriel, of course, have an exam. Go, take care. Good luck. You could go if you're busy. That's always fine. Okay, Kirill, good. Steven, good. The inverse function is itself, right? The function is canceling itself. How do I know? Well, here is the slow process, right? So we are labeling y as the inverse. And if I plug into my function the inverse, 1 over y will equal to x. It looks like I swapped variables, right? But really, again, this is what I did. I plugged into this function the inverse, which is y, and that's 1 over y, and that's supposed to give you back the input x. It's supposed to undo. So 1 over y equals to x means y equals to 1 over x. So the inverse is itself. The function cancels itself. Now solve for c. What's the inverse for c? All right, let's solve it together. Already, so for C, we can do it this way again, right? So 5 over y minus 1 is equal to x. You understand why? I plug, that's just my inverse. So what happens then, I just very simply solve it. So I take multiply by y minus 1 and divide by x. So this is what I get. Y equals to 5 over x plus 1. You see, just you can divide by 5, it would be 1 over y minus 1. Flip it over, so it's 5 over x equal to y minus 1. Add 1, it's 5 over x plus 1. And you can write it as 5 plus x over x if you prefer. If you have questions about the exam, yes, stay after class. I actually haven't uploaded it, but we can think of the question. Okay, I should upload it to my website. Okay, let's do one more. What do you say? Can you take the inverse of x cubed? Do D. And then if you have questions about the exam, stay after class. We'll deal with it. That's right, Ibad. That's right, Kirill. And if you are still here, guys, we started a little bit late. So let's also do problem D. Problem E, I'm sorry, right? Okay, Irvin, interesting. So guys, we're solving problem E, correct? Interesting. All right, let's solve it. So for D, you all got, I think, the cube root. That's pretty simple. Just it's y cubed equal to x, so y equals to the cube root. For the last function, it's just what you have is y minus 1, y plus 1 equal to x, where y is the inverse function. And then you, here is how I solved it. There are many ways actually to do it. But I would have liked to see a plus 1 on the numerator and denominator. So what I do is I say y plus 1 minus 2 divided by y plus 1. Then I can cancel it and write 1 minus 2 over y plus 1 equal to x. You understand? It's because why do I do that? Is because if it's the same on numerator and denominator, I would cancel it to 1. And y minus 2 because I have y minus 1. So if I want it to be y plus 1, I have to subtract 2. I cannot change the expression, yes? So then I divide the denominator into y plus 1 and minus 2. And you see what the benefit is now I only have one copy of y. I used to have y, and now I only have one y. And then I move things around, solve, and I get y equals to 1 plus x over 1 minus x. That means that my inverse is 1 plus x, 1 minus x. You see, the trick was to have fewer y's. Here I had 2 of them. Now I was able to get only 1. You see why that helps? And then I move things about, like what I show here. And that's just algebra. All right, so let's call it a day for this lecture. I'm stopping the recording. If you have questions, just stay during office hours.